Hey everybody. Well, I hope you can get yourself excited to do some theory here. Lecture 21, just like lecture 20, is going to be pretty theoretical, but that is important. Starting in lecture 22 and afterward, we're going to get into the practical interpretations and applications of general linear regression models, also called multiple regression. But we need to do some more theory. Theory is worthwhile. I think it's kind of fun, at least once you start to get into it and really start experimenting, including with Mathematica and spreadsheets, to try to confirm the theory. Secondly, it can give you insight. It can help you see connections between different topics. It can even help to unify topics and simplify topics when you do it correctly. And it can help you be a better problem solver for applications too. Okay? So for all those reasons, I think it is still worthwhile to do. We will not fully justify everything, but we do want to try to gain understanding at the theory that will help to unify things and help to justify things somewhat. But you do need to think about things in the right kind of way, so try to get yourself ready for that. All right, here's the lecture plan for this lecture. It's going to be about properties of least squares estimators in these models, and then we will apply it to interval estimators at the end. Lecture plan starts with the example from lecture 20. I forgot in lecture 20 to make a graph of this example, and I think I should have put that in lecture 20. Well, we will rectify that here and show it to you in lecture 21. And we will also, at the very end of this lecture, look back at it again and apply the interval estimation theory to that example. We will then talk about, very quickly, the matrix vector form of the general linear model and normal equations, as we've talked about a lot. This is the main part of this lecture. We'll look at properties of the least squares estimator vector. We're going to think of the unknown parameters beta 0, beta 1, beta 2, etc. as an unknown parameter vector, and we're going to try to estimate that and understand the properties of the estimators. Is it, for example, unbiased? Is its mean equal to the population vector? The answer is yes. Is it consistent? We'll find a formula for what's called the variance covariance matrix, which is a new idea. And note that its entries decrease to 0 as the sample size n increases, though we will not prove that. We'll see that it makes some sense, though. See, I will also add in some notes of things we've talked about already. SSE, SSR, SST. SSE is sum of squares of errors, which means residuals. SSR is sum of squares for regression itself. And SST is sum of squares total. I also called it SSYY. And we've talked about the coefficient of determination before, r squared. Well, in multiple regression, there's something called the coefficient of multiple determination. We'll look at the normality of the components and the nature of the corresponding standardized statistics when you need to use the z or a t table, for example. We also need the variance of the components to be able to calculate those things. Then at the very end, we will look at the application, interval estimation, for population regression parameters, trying to come up with confidence intervals essentially to estimate beta 0, beta 1, beta 2, etc. We'll look at the formulas in terms of sample statistics and quantities that can be determined from the inverse of the matrix of the solution of the normal equations. That's a mouthful, but you've seen this before. That's x transpose x inverse. And then we'll look at the final answers for these intervals from the lecture 20 example. We'll look at some spreadsheet output and the formulas themselves to see what the answers are. All right, so here let's start by looking at the general linear model example from lecture 20. Here was the model. The general model was that mu, when you know x1 and x2, this is going to be the mean of the y values. When you know x1 and x2 is some fixed function of x1 and x2, beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 times x1 x2. And this is a general linear model in spite of the nonlinearity here with the x1 times x2. And what I did was I took the betas to be known when I generated data with Mathematica. I took beta 0 to be 5, beta 1 to be 3, beta 2 to be 2, and beta 3 to be -1. Then I had Mathematica do some random sampling based on this part of the model where capital E are those E1 through En are independent and identically distributed random variables that are each normal with a mean of 0 and a variance of 3 squared, which is 9, which means, of course, the standard deviation is 3. What did I get for the sample regression line? Well, for one run of a sample of size 12, I got this sample regression line, 2.72 plus 4.24 x1 plus 2.83 x2 minus 1.73 times x1 times x2. So 2.72 is your estimate for 5. It's not real close, but that happens sometimes, especially with small sample sizes. 4.24 is the estimate for 3, 2.83 is the estimate for 2, and negative 1.73 is the estimate for negative 1 in the parameter model. Here is the graph, okay? And so you can see the black dots of the data, three-dimensional data, because you have the two explanatory variables, x1 and x2, and the one response variable, y. You've got to plot these points in three-dimensional space. The x1 axis is coming out of the screen at you, the x2 axis is going to your right, and the y-axis is going vertically. There's probably pretty much no way you could just look at those points and know that you'd want this kind of model to necessarily be the best idea. That was how the data points were generated, but you wouldn't necessarily know that. You'd probably, in general, try a simpler model where the equation would be linear, not just in the betas, but also in the x's. But this nonlinear model in x, which is a linear model in the betas, is the best model to use because it's how I generated the data in the first place. And the red curved surface is the graph of mu. The blue curved surface is the graph of y hat. And you can see the blue graph is supposed to be approximating the red graph. The green vertical lines are from the points to the blue graph. There are the residuals. When they are above the blue graph, you get a positive residual. When it's below the blue graph, you get a negative residual. But the point I wanted to make here is this is a nonlinear equation in x1 and x2, so you should not get a plane. Okay? All right, what's the matrix vector form for the general linear model in general? And we will come back to the example again at the very end of this lecture. This is even more general than I've talked about so far. And again, like I emphasized at the beginning, you want to think about this in the right way. The key to understanding abstract ideas, besides just having good skill with abstract thought and symbols, is thinking about them in the right way. That really is key. So we have our general linear model. We've got k explanatory variables, x1 through xk. We're pretending in our minds that these are fixed numbers, okay? When we think about this model here initially, at least. And then for any fixed values of those things, the mean of the y values, that's what we're talking about here with this notation, the mean of the y values, all the y values you could possibly observe for those given fixed x values, is assumed to be a simple expression involving the x's. A linear expression in the x's, also a linear expression in the betas. Now, like I mentioned, I think it was in lecture 20, these individual x's could depend in a nonlinear way. For example, x3 could depend on a nonlinear way on x1 and x2, for example. That's possible. Okay? Just realize that in the back of your mind. These variables are not necessarily varying independently of each other in this model, though that's sort of the simplest way to think about it. And then we have the individual y values themselves, the individual responses, again for fixed values of x. We're using the subscript I now because we're thinking about the ith data point. The first coordinate of the ith data point is x1i. The second coordinate of the ith data point is x2i, etc. The kth coordinate of the x data point is xki. We've got this linear expression in those values based on the betas, but then because we're talking about individual responses for y, not just the mean, we need to add on this error term, a random residual, you might say, that can be positive or negative. You know, it would make sense with equal likelihood. Yeah, you'd want the EIs to be centered on 0, and in fact, we usually have them have a common distribution that is normal. It's a normal distribution with a mean of 0 and a variance of sigma squared, which of course then means the standard deviation is sigma. All right, so that's the background model for this. Now we're going to think about this with vectors. Okay, this is somewhat similar to what we already talked about with normal equations and the design matrix, for example, but there is some extra generality here. I'm letting y be a random vector because it's a vector of random variables. Okay, so those individual y's that are not bold-faced are the individual response variables that are scalars. I'm putting them in an n-dimensional vector. This matrix is dimension n by 1. I can think of it as an n-dimensional column vector if I want, and that's the way I usually think about it. Okay, that's the first generality we're going to talk about here. The second thing is these parameters we're also going to put in a vector. Beta 0, beta 1 through beta k. And since we're starting with beta 0, this would be really a k plus 1 dimensional vector. or as a matrix, you could call it k plus 1 times 1-dimensional. I wanted to make this beta right here bold-faced in the PowerPoint, but the PowerPoint would not let me make it bold-faced. It's bold-faced in the textbook that I used for this class right here. I wanted to make it that way. It just wouldn't let me. I did make it a little bit bigger than the other betas to try to emphasize that it is a vector. And we can even put the errors in a vector, E1, E2 through En, etc. And I made that bold-faced. It let me do that. That's an n-dimensional vector. As a matrix, it's n by 1, n columns and 1 row. Right? Excuse me, n rows and 1 column. Then in this context, you can write the design model very succinctly like this, the model. Y equals x times beta plus e. That's essentially taking this equation n times and putting everything in a vector, where x is the design matrix and it equals this that you see right here. And again, this is still more general than we've talked about so far. So far we've focused on specific examples, though I've tried to up the generality as we've gone through the examples. Once again, the design matrix has all ones in the first column. In the second column, you see x11, x12, x13, etc. through x1n. These are the first coordinates or components, you might say, of the n data points. First components, first coordinates of the n data points. The next column is the second coordinates or second components of the n data points, x21, x22, x23, etc. through x2n, etc. You got k components for the data points. The last column here is the kth entries of the n data points, xk1, xk2, xk3 through xkn. And again, the subscript notation here is inconsistent with the usual kind of subscript notation for the entries of matrices. Don't let that confuse you, okay? The x1s, where the 1 is the first thing, corresponds to first coordinates. The second numbers, 1, 2, 3 through n, corresponds to which data point you're looking at. This matrix has n rows and k plus 1 columns. It's good to, if you haven't written these things down, to go ahead and write these down and keep these dimensions in your mind as we go. That helps you understand the abstract ideas. Let's quickly talk about the normal equations for a given observed data vector y. So here I'm using a lowercase y. I'm about to use an uppercase y again in a little bit here, but I'm using a lowercase y to emphasize I'm thinking of this as an observed value of capital Y. Observed data vector. So we've actually gathered data about y. We can write the normal equations in this way. We've talked about this with examples in recent videos. X transpose times x times the unknown b, which is going to be your vector estimate of the beta vector. This is a statistic. The beta vector is a parameter. We want to solve the system for b. We want to estimate beta by solving the normal equations for b. We can write the estimate in various ways. Okay, ignore this part for the moment. Focus on this. We can think of b as being this vector, b0 through bk. And how do we get from here to here? We just multiply on the left both sides by x transpose x inverse. Okay, and that's what you see here. It cancels with this thing on the left to give in the identity matrix times b, which is just b. And you have to do it on the right as well. And this cannot really be simplified because x and x transpose, unless it's a real simple situation, are not going to be square matrices. Their product, x transpose times x, is a square matrix. And if you've got at least two distinct x values, it's going to be invertible, so we can take its inverse. But we can't bring the inverse through here, okay? We can't use something called the Sox-Choose property to bring the inverse through there. It's as simple as it can be. I'm also calling this now beta hat, where again, I wanted to make that beta boldface. It is a little bit bigger than these. This is a vector. Beta hat 0, beta 0 hat, beta 1 hat through beta k hat. What is this? What's the beta hats? It's just emphasizing that these are estimates for beta. You know, in statistics, we often put hats above variables when we're emphasizing that these things are estimates or predicted values of an unknown parameter. Both notations are used, including both notations in the book that my class uses. So I want to talk about both, and it's good to be aware of both notations. Okay, don't let that bother you. Be flexible in dealing with this abstraction. But we can also think about this as an abstract estimator. Here I'm thinking of it as being an observed, sample statistics. B0 through BK or beta 0 hat through beta K hat are observed sample statistics based on little y being an observed output vector. But if we want to think about it theoretically, we can think about this equation as an abstract estimator. And in that case, I kept the beta's notation the same, but with the b's, I would more typically write a capital B here and capital B's in there to emphasize that these things are really random variables. They have distributions even. We can find expected values and variances for these things. And notice I put a capital Y here as well. Again, because I can think of the individual y's as being random variables. Capital Y1 through capital Yn. Okay? I kept the beta notation the same. Don't let that bother you here. Here I'm thinking of them as being observed values. Here I'm thinking of these things as being theoretical estimators. All right, so what are some of these properties of these things that we're interested in knowing and would be good to know? Is capital B, beta hat, as an abstract estimator, a good estimator? Well, what does that mean? Well, for one thing, it should mean, is it unbiased? Does the expected value, this E here means expected value, expectation, not error. Another point of difficulty in dealing with abstraction is sometimes the notation is inconsistent or conflicts even. The E so far is represented an error, a residual. Here, E represents expectation or expected value. Is the expected value of beta hat as an estimator, as a statistic in an abstract sense that's got a distribution, or in this case a distribution for each of its components, equal to the vector beta itself, the unknown parameter vector. That's just a vector of numbers. They're unknown numbers, but it is a vector of numbers. Is that true? Okay. Is it consistent? Does the variance of beta hat somehow go to 0 as n goes to infinity? So if it's got an expectation, does it have a variance too? But really there's another question we should answer before trying to answer these questions. What in the world are the meanings of the expectation and the variance in these contexts? Are they numbers? Well, no, they can't be numbers. The first one, in fact, has got to be a vector. What about the second one? What about the variance? That's actually going to be a matrix. That's not just a column vector. All right, so let's talk a little bit about those generalities here. For a general random vector, which is a vector of random variables where the components are random variables, call it capital Y, and I'm not talking necessarily about least squares here when I talk about this. What's the expected value of that vector? You take expected values as you would guess you would, component-wise. The expected value of capital Y as a random vector is done component-wise. You get a new vector whose components are all those expected values, and I see a little typo here. This n should really be in here. Okay? A new vector whose entries are all these expected values, which are all numbers, so this is going to be a numerical vector for a given random vector, capital Y, boldface. Okay? Is that a good idea to define the expected value of the Y vector this way? Well, we will see that it is a good idea. Okay, at least in this context. You know, definitions are never true nor false. They are either good ideas or bad ideas. We're going to see it's a good idea in this context. So what's the expected value of the error vector? So here, there's funny, it's the expected value of the error vector. This means expectation, this means error vector. The vector E1, E2 through En. You just take the expected values of each of those individually. But wait a minute, I said each of those individually as a set of vectors forms an independent and identically distributed random variables set of vectors and random samples, so to speak, that all have the same distribution that was normal with mean 0 and a variance of sigma squared. The mean of these things is all 0. You get the 0 vector out. Okay, so that vector has an expectation that's the 0 vector, which again just means the expected values of all the components are all 0. And if we now think about y, we can take the expected value of y as the expected value of this thing, and is there a linearity property for expectation in this case? Yes, there is. Am I proving it? Well, not really. you could think about it component by component. It's not too hard. Expected value of y, which is the expected value of this thing. I can break the expected value of a sum into the sum of the individual expected values. I can then use the fact that the expected value of e is 0, and this thing is a constant. That's a constant vector. And so its expected value is itself. So you get the expected value of capital Y is x times beta. Is that really right, or does that really make sense? Well, let's think about it in the context of simple linear regression here in a second. Does this really work? Yes, the expectation operator is still linear. It's a linear operator when working with random vectors rather than just random variables. As an example to illustrate it, let's think about it for simple linear regression. Essentially, this equation here, that the expected value of y equals x times beta, in the context of simple linear regression, is just confirming a confirmation of this fact here. Simple linear regression, again, you only have one explanatory variable, x, not more than one, not an x1 and x2, etc. We have just a beta 0 and a beta 1. Yi is, there's the mean for the given xi, and here's your random variation for the n data points. And if that's the case, we have seen before that this is true, okay? In fact, it's an assumption we're making, and we're really making the same assumption here, based on the assumptions we made about x and beta in the original model. And this is just a notation for the mean, the expected value. If you think about this example with simple linear regression in terms of matrices, the design matrix is simple, just 2 columns, all ones, and then x1 through xn. And beta is, as a vector, is just 2-dimensional, beta 0 and beta 1. And if you multiply x times beta, you get beta 0 plus beta 1 x1, beta 0 plus beta 1 x2, etc. through beta 0 plus beta 1 xn, which is going to match this, of course, and it also really matches this component by component. Okay? So it does make sense in the context of simple linear regression. It's another way to try to think about why things make sense. Therefore, okay, here's where it starts to get extra tricky. So think about the normal equations and their solution. We took x transpose times x inverse times x transpose times y. So we can talk about the expectation or expected value of beta hat as an abstract random vector. Beta hat, that's a vector. It's beta 0 hat, beta 1 hat through beta k hat. It's a k plus 1 dimensional vector. What's its expected value? Here's where I use the formula I just mentioned a minute ago. That beta hat, which before we really called boldface B, is x transpose x, quantity inverse, times x transpose times y. And then this is a constant matrix that can be factored out of the expectation here. This is also a linearity property. I'm not really proving it, but that's true. You can maybe check it with simple 2-dimensional examples or something like that to try to see how this does work. Maybe try particular numbers for the x matrix. And then you can replace the expected value of y with x times beta. And then you can rearrange a little bit. You can use the associative property to group x transpose times x with, well, this x transpose with this x, and keep the beta over here. And then stare at this and say, hey, wait a minute. This is x transpose times x inverse, and this is x transpose times x. If I multiply those, I have to get the identity matrix. I do. I, where I is the k plus 1 times k plus 1 identity matrix. Right? Why is it k plus 1 times k plus 1? Well, x transpose is, well, x itself, I need to remember, is, I'm forgetting, n by k, x transpose is k by n times n by k is k by k. Excuse me, said that wrong. N by k plus 1. K plus 1 by n times n by k plus 1 is k plus 1 by k plus 1. Okay? Write that down. Beta is k plus 1 dimensional. Multiply I times beta, you get beta. Hey, Expected value beta hat is beta. That means beta hat is unbiased. That's what it means to be unbiased. The expected value of the statistic as an abstract estimator equals the parameter you're trying to estimate. All right, what about the variance? Well, we need to kind of build up to that. Given a general random vector, capital Y, y1 through yn, and again, this doesn't necessarily mean we're thinking about least squares linear regression here. We can define something called the variance covariance matrix. That's the way our book describes it here, my book that I'm using with my class. But I looked online and all other people call it different things. Sometimes people call it the variance matrix, and sometimes they call it the covariance matrix. Probably is best, I think, to call it the variance covariance matrix because as a matrix it contains both kinds of quantities, though those quantities are related to each other. Covariance is just a generalization of variance. It's this matrix, an n by n matrix, where n is the number of data points. The entries on the main diagonal are variances. Variance of y1, variance of y2, variance of y3, etc. through variance of yn. The entries on the off diagonals, or the numbers that are not in the diagonal, are covariances. Covariance of y1 and y2 here and here. This is a symmetric matrix. Covariance with y1 with y3 here and here. You could switch the order of those around inside the parentheses because covariance as a function of its two inputs is symmetric with respect to those inputs. You can switch them around. Covariance of y2 and y3 here and here, etc. Covariance of y3 and n here and here, for example. There's missing entries. It's n by n matrix that we're going to call the variance covariance matrix. We'll use both words. We will use the variance notation for it, again, because that's what our textbook does, though you can find online some people call it covariance of y. Don't let that bother you that different people use inconsistent notation and terminology. It's okay, it's the idea that's important. Just realize that happens sometimes. There can be inconsistencies. In the context of our general linear model, this simplifies quite nicely. To a diagonal matrix, in fact, it's a constant multiple of the identity matrix. All the covariances of the distinct y's are 0 because we're assuming those are independent of each other. That's the assumption, an assumption that's part of the model that comes from the EI's being assumed to be independent. The errors. So all the entries off there are 0, and in fact all the entries in the main diagonal are the same. They're all sigma squared because we assumed all the EI's had a variance of sigma squared. The y's are going to have variances of sigma squared as well. There we go. And this is this scalar sigma squared times this matrix I, the n by n identity matrix. Identity matrix has 1s all in the main diagonals and 0 everywhere else, if you didn't know that. Okay, so it simplifies pretty nicely in the context of our general linear model. That's good. Anytime something simplifies, it's a good thing. We need a general fact about the variance of these n-dimensional random vectors before we can apply it to the general linear model. If y is an n-dimensional random vector and C is an m by n constant matrix that's going to play a role of a constant, then the variance of C times y, really the variance covariance matrix, is this product you see right here. This is a product of matrices. Keep track of the dimensions. That's so important for your understanding. C is m by n, and y is n by 1. C times y would be an m times 1 vector. Its variance covariance matrix would then be m by m. That's going to be dimension m by m. This thing on the right also better be dimension m by m. Well, again, C is m by n. The variance covariance matrix of y is n by n. We can multiply m by n times n by n. This is the transpose of C. That's n by m. So the product can be done, and the answer is going to be m by n. This is a generalization of the fact that the variance of a constant times a scalar random variable is the constant squared times the variance of the scalar random variable. The C over here and the C transpose are, in a sense, a squaring of C, but you have to do it in this way to make the dimensions work out. Now, it's not obvious that this is true. You should double check it with an example, say a two-dimensional example. Y is a two-dimensional random vector and C is 2 by 2. Give it a try and see that it works. Therefore, now here's the hardest theoretical derivation we need to do, okay? So roll up your sleeves, get ready, get psyched up here. Just take it step by step. This can be done as long as you think about things clearly. What's the variance of beta hat? Beta hat, remember, is essentially boldface B. It's our estimator. For beta, the beta vector, that's a constant but unknown vector. By solving the normal equations, beta hat is this thing, where y is now as an observed vector but thought of as a random variable. All right, well, according to this fact up here, I can take this constant matrix that's in front, put it on the left here, and it's transposed on the right here, and in between I have the variance covariance matrix of y. Okay, so that's just using the equation in red in the first step. This gets even trickier here. What's next? How in the world can you possibly simplify this thing? Well, remember, you cannot bring the inverses through the parentheses because x and x transpose are not squared. But it turns out you can bring the transposes through the parentheses, this one in particular, as long as you swap the order of these things after bringing it through. And that's a similar property like that holds with inverse matrices when you're talking square matrices. These are not square matrices, so you can't do that with inverses, but you can do it with the transpose. So that's what I did here in this line. That's one thing I did. As you see, I take this thing, x transpose, and take its transpose, which gives me x, and put it on the left right there. When you transpose a transpose, you get back the original matrix, which should make intuitive sense. Transposing means swapping the rows and the columns. You do it again, you're going to get back the original matrix. I also did it with this matrix here, including the inverse sign, and that's what you see here. I also use the fact that for our general linear regression model, the variance-covariance matrix, as we saw, simplifies to a constant multiple of the identity matrix. The constant here is sigma squared, which is the assumed variance of the original error terms. All right, so that's the previous page. That's the sigma squared I and properties of transposes. Keep going. What else could we do? Well, we could get rid of the I. Here it's an identity matrix. The sigma squared can be factored out in front. It's a scalar. I will do that, though not quite in this step. In the next step, what I do here is I simplify this thing. It turns out the inverse symbol and the transpose symbol can be interchanged. That's a property of transposes and inverses. So I did that swapping right here. I put the transpose here and the inverse up here. I also got rid of the identity matrix, just wrote an X here. Next step, I'm going to bring the sigma squared in front, and one other thing, I'm going to rewrite this expression. Once again, transpose over product. You bring the transpose through and you swap the order. But with a special kind of matrix like this, x transpose times x, when you swap the order, you get an x on the left and x transpose on the right. And when you take the transpose of x transpose, you get x transpose. And when you take the transpose of x transpose, you get x. I don't think I said that right. When you take the transpose of x, you get x transpose. When you take the transpose of x transpose, you get x. It's not quite as hard as it sounds there. I put this x on the left and took its transpose. That's this. I put this x transpose on the right and took its transpose and got back to x. Okay? Kind of confusing, but that's what happened. And I brought the sigma squared in front. What should I do with this? Well, I see x transpose x, quantity inverse. I also see an x transpose times x there. I should use associativity as a step sometimes people don't bother showing to say I've got this times this, including the inverse sign. These cancel to give you an identity matrix like this. And we get a final simplification to this. That's the variance of beta hat, which is really the variance covariance matrix. Beta hat is a vector. Its variance is really a variance covariance matrix. It's sigma squared, that constant, times this matrix. Okay? Is beta hat consistent? Not going to prove it, but it should make some sense that the entries, the individual entries of this matrix, should get smaller as n increases. I'm not proving that here, but I hope that makes some intuitive sense. As n increases, you're adding more data points. X is becoming a bigger matrix, a taller matrix. Remember, X is n rows and k plus 1 columns. As n gets bigger, you get a real tall matrix. You're adding more to X. X transpose times X is probably going to involve really big numbers. And if you think about the summations we've seen in recent lectures, that's certainly true. I hope it makes some sense that its inverse matrix probably then involves some pretty small numbers. And they get smaller in general as n increases. This is by no means a proof. But that should make some intuitive sense that that probably happens. So yes, this beta hat is a consistent estimator in addition to being unbiased. Turns out an unbiased estimator for sigma squared is called S squared, the regression standard error, with simple linear regression where k was 1, we did SSE divided by n minus 2. Here it's SSE divided by n minus k minus 1, which you can also think of as n minus in parentheses the quantity k plus 1. Right? With simple linear regression, k is 1, your design matrix is n by 2, k plus 1 is 2, we have SSE divided by 2. You add on another explanatory variable, so k is 3, we'd be dividing by n minus 3. You add on another explanatory variable, which could be like x1 times x2, like in our example at the beginning. For example, it could be a nonlinear in the x's equation. K would be 3 in that case, so this would be dividing by n minus 4. I'm not going to prove this is unbiased, because the proof is real unpleasant. We're trusting it. Maybe if we have time, we'll do a simulation that verifies that something like this is unbiased. Through simulation, that's not a proof. This is what happens in multiple regression. Our corresponding estimate for this variance covariance matrix, denoted by variance of b hat, you might say will typically approach the zero matrix as n grows larger. Why do I say typically? Well, I mean, certainly you're dividing by something bigger and bigger as n gets larger here. But SSE is going to get bigger and bigger too. Does the bottom win out, so to speak, over the top, making this get smaller? It will typically, but I'm not going to verify that. Can also be shown that SSE, our old friend, sum of squares of errors, residuals, is SSYY, which I've also called SST, sum of squares total, minus SSR, sum of squares regression. I did mention this in the context of simple linear regression before. I think it was lecture 17. It might have been the first video I made for this course, spring of 2020, where I emphasized that one over the second one. Where SSYY, again, means SST. It's the variability of the data about the mean. It has nothing to do with regression. SSYY, sum of squares of these y's, has nothing to do with regression. It's related to the variance of y, actually, standard deviation of y. If you divided this thing by n minus 1, it would be the variance of y. If you took the square root of that, it would be the standard deviation of the y's. You can compute this without thinking about regression at all. Turns out that's also equal to this. I've mentioned that before as well, in lectures 1 and 2, I believe, which are really 17 and 18. The first and second ones I've made videos for. And SSR measures the variability of the regression line about the mean of all the y's. This yi hat here, not a yi. Turns out you can verify with a lot of work that equals, in this general context, this expression minus this one, where these capital B's are the individual estimators for beta 0, beta 1 through beta k, which are scalars. These are all scalars here, not vectors. Okay? Should be able to verify that. Well, actually not verify that equation, but use it. Let me point out to my students that in the book, an example you should make sure you go through and be able to confirm and be able to do for homework or a test is example 12.3.3. It's page 468. The example here that gets into the details of this thing for an example. 12.3.3, page 468. And we also write the SST equals SSE plus SSR. Dividing everything by SST, we can also say 1 equals SSE over T plus SSR over, I should say SSE over SST plus SSR over SST. And this fraction here, we give another name, we call it R squared. And here in the context of multiple regression, we call this the coefficient of multiple regression. Multiple determination, I should say. It was just the plain coefficient of determination in simple linear regression. Just make sure my description is consistent with the textbook here. Yeah, coefficient of multiple determination. It's going to be between 0 and 1, because SSR is going to be between 0 and SST. Closer it is to 1, the stronger the linear trend is for the general linear model in this case. The closer this is to 1, the closer this is going to be to 0. When this is close to 0, SSE is very small, not much variability about the regression equation and its graph in higher dimensions. SSR, the variation about the regression line completely or very close to explains the variability in the y values. Okay, hang on with me. Getting close to being done. Still more important things to do. In addition, each component of this estimator, beta I hat, which we also call capital B I, of beta hat, beta has the vector, the beta I and bi are scalars, has a normal distribution because of our assumptions. Okay, we assume the errors, EIs, had normal distributions, therefore the YIs have normal distributions, and this equation, solving the normal equations this way in the abstract, implies that each bi, beta I hat also, is a linear combination of the components of y. That's what it means to multiply this matrix times this vector. And linear combinations of normal random variables are also normal. You can use the fingerprint theorem to prove that. In our textbook, it's back in chapter 7, involving moment generating functions and how they identify random variables. Also, the variance covariance matrix of beta I hat, excuse me, not matrix, this is a scalar, sorry. Beta I hat is a scalar. What's its variance? It can also be written as variance of capital BI. Is CII times sigma squared, where what is CII? CII is the entry on the main diagonal in row I plus 1, and therefore also column I plus 1, of this matrix, which is a square matrix. X transpose X times inverse, which is this thing here as well. Why? Well, it was because the variance covariance matrix of beta hat itself was diagonal with the sigma squareds on the main diagonal, sigma squared times capital I. And also, well, that was for y in our case, but in our, it was this fact here. So it's sigma squared times X transpose X inverse. That's not necessarily a diagonal matrix, but it turns out that these CIIs in this other slide here are those entries. Should make intuitive sense. Therefore, if we try standardizing our statistics to estimate the betas, take beta I hat, which I'm also calling capital BI. I'm just rewriting it here in two different ways. You should be comfortable with either. Subtract the mean, which is going to be beta I because it's unbiased, and divide by the standard deviation, because the variance of the beta I hats are these things. Take the square root of that. You're going to divide by the standard deviation. You can write either fraction. Those are all standard normal. Mean is 0, variance of 1. And if we replace sigma by its estimator, S, and by the way, remember S squared is unbiased for sigma squared. Actually, S itself is not unbiased for sigma, but we won't worry about that. So I'm replacing the sigma with S's here, these regression standard errors. This equal sign should not be there. I get a random variable that has a t distribution with n minus k minus 1 degrees of freedom. Just like in computing s squared and s, we divide by n minus k minus 1. Okay, I'm not proving this. This should make intuitive sense based on what you've known from the past and doing similar kinds of things. So we could use these statistics to do hypothesis testing. I'm not going to do that here. To finish this video, we will apply this to interval estimation with these formulas. Then we'll look at the computer, Mathematica, and spreadsheet to see that we got the right answers. Let's go back to the example from lecture 20 and also the beginning of this lecture, lecture 21. What is a confidence interval to estimate a population parameter, beta I? Which we could do for k plus 1 values of I equals 0, 1, 2 through k. So we could try to estimate beta 0, beta 1, beta 2, etc. It's your point estimator, beta I hat or bi, lowercase bi. Actually, I should call that uppercase. That's a typo. Let's change that right now so I don't forget. Lowercase bi would represent an observed value. So these are just two different symbols for the same thing. Statistical estimators. Plus or minus a margin of error. And the margin of error is always the same kind of type. It's like a z or a t value. In this case, it's a t value with n minus k minus 1 degrees of freedom, which I should have mentioned here, but I forgot, times the standard error, s times the square root of CII, because that's your estimator for sigma times the square root of CII, where CII, again, is an entry on the main diagonal in the I plus first row and also I plus first column of the matrix. Oops, sorry. Where is it here? Here we go. Oh, the matrix X transpose X inverse. Right here. Okay. Hang on, we're almost done. Mathematica, I used Mathematica to compute X transpose X inverse and got this. I will show you the code here in a minute. So I'm looking at the main diagonal numbers here. These things are the CIIs. C00 is 3.5, C11 is 0.75, C22 is about 0.46 repeating, probably exactly 0.46 repeating, but we're rounding it to this. C33 is 0.1. That's what I have here. Also, from either Mathematica or spreadsheet output, you can find the regression standard error. Its observed value turns out to be about 3.64618. Notice I'm dividing by n minus 4 in here, because k is 3. So n minus k minus 1 would be n minus 4. And what are the answers? We're going to use t sub 0.05. I guess, excuse me, is that the right number to use as well? That would be t sub 0.025 if I use the right number in the table. So we got 8 degrees of freedom. Yeah, that should be t sub 0.025. Another mistake that I need to fix right now. Which would be the t value you use for 95% confidence. Come on, here we go. Let me edit this thing. Here we go. Because alpha is going to be 0.05. Here are the answers, okay? And it's using the formula in the previous slide. Notice that all of them contain both positives and negatives. They all contain 0. So if we were doing two-tailed hypothesis tests for any of the parameters, beta 0, beta 1, beta 2, and beta 3, we would not be able to reject the null hypothesis that they equal 0. So that's maybe disappointing. You might hope to reject the null hypothesis to even do regression in this context. It's because the sample size is so small. N is 12. Even with doing the simulation on Mathematica, I'm not getting statistically significant evidence against the null here. Pause and write these down. I'm going to then show you some things in Mathematica in the spreadsheet to end the video here. So you got it written down. That is the last slide. Okay, so here was my my data. x1 varied from 1 to 3, x2 varied from 1 to 4, and whole number values. The decimals are the observed y values for one particular sample run of size 12. I got this regression, observed regression equation called y hat. Here, by the way, is the graph as well. Same graph I showed you in the PowerPoint. Nice thing about Mathematica is we can now rotate this to see that those green lines really do go to the blue graph instead of the red one. A little easier to see. Got the design matrix normal equations. I'm going to jump down to, oh, by the way, maybe we want to see the entries of x transpose times x inverse are small. Yes, those are relatively small numbers. And these are the numbers that I got that you just saw in the PowerPoint. 3.5, 0.75, 0.46 repeating, and 0.1 of this C00 through C33. But I want to go to linear model fit. And again, when you enter this, you don't really get any output besides this, but you can do other things. And in particular, we can do an ANOVA table. And the thing I want to highlight here is this number, 106.357, is SSE. I divide that by n minus 4, which is this 8 degrees of freedom, and I get a mean square number. MS stands for mean square of 13.2946. It's the square root of that is the regression standard error. S is about 3.64618. And I can do confidence intervals for the parameters. Let's see. With this will be the parameter one. No, that's the p-values for a test. Where are the confidence interval tables? Is this it? There we go. There's our confidence interval. So this is your confidence interval for beta 0, about -13 to 18.4. Is that consistent with what we got here? -13 to 18.4. So some rounding errors because of just rounding to different amounts. This is your confidence interval for beta 1, this for beta 2, and this for beta 3. These, by default, are 95% confidence intervals. We can change the confidence level to 99%, for example, and get bigger intervals, though these are just the intervals instead of the table here. But like this is a 99% confidence interval to estimate beta 0, for example. And then, yeah, let's confirm one of these. This is about -4.4 to 0.9. Yeah, -4.4 to 0.9 or so. And then let's look at the spreadsheet to finish things off. Notice here is regression standard error. N is 12. Here's SSE divided by n minus 4. Gives you 13.29. It's the square root of that equals this. Here are your coefficients. B0, B1, B2, and B3 as estimates for beta 0, beta 1, beta 2, and beta 3. And your confidence intervals, these are the same kind of confidence intervals that we already saw. So next time we'll get into practical applications, which does include hypothesis testing based on t-statistics and p-values. We're really going to focus a lot in coming lectures on practical applications and interpretations. Thanks for watching.